Good morning, everyone. I am Holly Casaletto, currently a graduate researcher at UC Santa Cruz. Thank you for joining me today for our case study of enhancing gRPC microservices in high-performance trading systems. This work was done in collaboration with my colleague Yucong during my time at Coinbase. I have since transitioned to shift my focus to my PhD work, which continues to explore optimizing RPCs for microservice performance. For today's talk, due to a scheduling conflict, Yucong couldn't be here, so I will be presenting our work solo. Let's start by outlining our agenda. So we'll first do a brief introduction on trading system with a focus on its single-thread model. Then we will be discussing the two gRPC usage enhancements we implemented, which are transitioning from unary to bidirectional streaming model and then replacing Protobuf with FlatBuffers. We'll also cover briefly our systematic approach in load testing those enhancements. And lastly, we would like to present our wish list for gRPC, Protobuf, and FlatBuffers that we believe could further enhance our system. So let's first do an introduction on trading systems. Trading systems are essentially performance-sensitive systems. Specific to Coinbase trading system, it's an application written in Go. It is engineered to process requests with ultra-low latency and extremely high throughput, specifically achieving sub-millisecond latency and processing over 10,000 requests per second. At the core of such system lies the matching engine, which internally uses a RAF cluster for its fault tolerance mechanism. Matching engine accepts order requests from the order entry, matches them, and then generate messages for those matching results to be disseminated to the downstream in the market. As performance is very critical for trading systems, effective trading system must be designed with the maximum efficiency of compute resource in mind at all time. Beyond performance, ensuring the correctness of transaction execution is crucial for trading systems. While there are concurrent threads inside the matching engine handling various tasks, to guarantee correctness, each task must adhere to a strict single-thread model during execution. This ensures that all transactions are executed sequentially and without risk conditions. But in the meantime, it also requires each task to be designed to execute with maximum efficiency, minimize CPU usage, pre-allocate memory whenever possible, and avoiding blocking situations. Here's an example of a simple gRPC usage pattern in trading systems. In fact, it was the model in place before our enhancement work. In this model, an order request arrives as a unary service call, prompting the creation of a separate server-side Go routine to handle the request. Given the heavy traffic pattern in trading systems, this straightforward model often results in tens of thousands of Go routines to be running simultaneously, leading to resource contention and thrashing. This also could cause the tail latency to spike, especially when a blocking Go routine has to wait for its turn to be rescheduled on the, randomly by Go scheduler on the CPU. This chart illustrates one of the key problems of the simple usage model we discussed in the previous slide, which is the increasing gap between the average and tail latencies when request volume is high. As you can see, when the request volume increases, the average latency remains relatively stable. However, the tail latency starts to rise significantly. The gap between the average and tail latencies become more prominent at higher throughput levels, especially when the system is handling over 8,000 requests per second. The widening gap indicates that while the majority of the requests are being processed within an acceptable time frame, there is a small but critical percentage of requests that are experiencing much longer delays. This could be particularly problematic in trading systems where timing is crucial, as these tail latency spikes could cause significant performance bottleneck and impact overall user experience. The cause of this issue lies in the thrashing problem we mentioned earlier. As more Go routines are created to handle the increasing volume of requests, they begin to compute for CPU resource, leading to more inefficient scheduling and consequently longer delays for some of the requests. The problem of the simple usage model is further demonstrated by these charts. Let's look at the top graph first. As number of clients increases, we see that the throughput initially rises and then it plateaus. The throughput plateau indicates that the system has reached its maximum processing capacity. So adding any more clients does not result in the corresponding rise in throughput. Essentially, the system is saturated. And now look at the bottom graph. We see that the tail latency starts to rise significantly around the time when throughput plateaus. The sharp rise of tail latency is a direct consequence of the system's inability to efficiently manage the growing load, leading to delays for some of the requests. The combination of throughput plateau and the sharp rise in tail latency clearly demonstrates the limitations of the simple usage model when scaled. The issue of this, the cause of this problem is the thrashing that we mentioned earlier. While the system is able to handle a moderate load effectively, it struggled at a higher volume, leading to significant performance degradation. Now let's dive into the details of our enhancement work. But before we discuss the transition from unary to the streaming model, let's take another closer look at the thread model in the unary approach. In this model, when an order request arrives, a server-side Go routine is spawned to handle the request by adding a notify callback channel to the request and then passing the combined struct to the order processing queue. After that, the server Go routine blocks until the response to the request is placed by this other order processing thread in the notify channel. As we mentioned earlier, this approach at times could cause a large number, sometimes basically unbounded number of Go routines to be competing for CPU resource, exacerbating the latency spikes. So we transitioned from the unary to the bidirectional streaming model by using 3 threads and 2 channels. 2 of those threads are blocking Go routines, with one responsible for receiving requests and sending back, the other sending back responses. The third Go routine basically picks up requests, process it, and put it in the response channel. And when, to avoid getting scheduled off of the CPU, when there's no request to process, it engages in busy spinning. And this approach resolves the issue of unbounded number of Go routines, and it delivers responses in the same order as requests come in, which help prevent unwanted tail latency spikes. As one of the blocking Go routine, the Go routine number 1 executes in this infinite loop. It exits gracefully when a termination signal is received. Otherwise, it continuously listening for incoming requests using stream.receive function. The function blocks whenever until a request is available, and after a request is received, it's placed in this channel, and after that, the Go routine immediately returns to listen for the next request. Go routine number 2, similarly, also executes in this infinite loop, and it retrieves a response from the response channel and attempts to send it using the stream.send function. The function blocks until the response is sent successfully, after which it immediately proceeds to retrieve and send the next response. The coordinator thread is a continuously active thread by either processing a request or engages in busy spinning when there's no request to process. It's connected to the other 2 Go routines via those 2 channels. The primary responsibility for the coordinator thread is to process requests. The busy spinning mechanism helps the coordinator thread to stay on the CPU such that it can pick up the request and process it without delays. And this helps the system to maintain a high level of overall responsiveness. The transition from the unary to bidirectional resulted in significant performance improvements. Unlike the unary model where the latency spikes when the throughput plateaus, the bidirectional streaming model continues to scale effectively. And the result indicates to us that the bidirectional streaming model is better equipped at handling higher throughput without compromising on latency. This is likely due to its ability to mitigate the resource contention and thrashing problem. Now let's move on to our second enhancement, in which we replaced Protobuf by FlatBuffers. The motivation behind the shift from Protobuf to FlatBuffers is to avoid the repeated serialization and deserialization of data across microservices. The top graph shows how data was handled in the trading system using Protobuf. As you can see, after data is serialized, it needs to be deserialized once more when it enters another microservice. And similarly, the deserialized data needs to be serialized when it needs to be stored in the storage system. And this cycle just continues. The repeated serialization and deserialization adds latency and overhead, CPU overhead to the system, leading to possible performance bottlenecks. Look at the bottom diagram, which shows the new approach using the FlatBuffers. So with the FlatBuffers, the need for repeated serialization and deserialization is eliminated. When the request arrives, There's no need to deserialize it, and instead data is directly accessed from the raw buffers. And later when it needs to get ready to be sent to the next microservice, it undergoes a simple repack operation, which is far less resource intensive compared to the full serialization process. And finally, when the data reaches the new microservice, it can be used and repacked as necessary without the overhead of deserialization and serialization. So having gone through the motivation, let's move on to the how. How did we do the migration? Well, first step, we translated field by field the schema generation definition file from Protobuf to FlatBuffers. And the second step is one of the most challenging and time-consuming steps in this migration process, which is to ensure that the migrated FlatBuffer schema is an exact match to the original Protobuf schema. As the internal data representation for these two differ quite significantly, there is no off-the-shelf tool that can verify this automatically. To address this, we invested considerable effort in this rigorous double-check process. We either write custom functions to convert these two to a common format such as JSON for comparison, or we write custom functions to directly compare them to verify that they represent the same data. So these checks are essential to maintaining data integrity throughout the migration process. So now, after thoroughly testing and validating the migrations, the schema migration, we proceeded to implement the code. On the client side, we added code to write data into the raw buffers. And on the server side, we implemented code to access data from the buffers. So this enabled us to fully leverage FlatBuffers' efficient zero-copy design. The transition from Protobuf to FlatBuffers also resulted in significant performance improvement across various stages of the request-response cycle. Notably, we saw a 7 times end-to-end latency reduction. This includes receiving requests and processing requests and sending back responses. So breaking down further, we saw 20 times improvement for receiving requests and 15 times for internal processing the messages and 2.5 times for sending back responses. Those results clearly demonstrated the efficiency gains achieved by moving to FlatBuffers. Next, I would like to briefly mention the systematic approach we adopted in load testing the enhancements. Pacing is the key technique that we introduced to simulate different real-world load scenarios. By varying the sleep duration, we were able to generate different levels of traffic load on the system. This enabled us to focus on observing how average and tail latency responded to under different varying conditions. And by combining the analysis of test data and a detailed system profiling, we were able to identify areas for improvement and effectively optimize our system using empirical data. This concluded sharing of our enhancement work to improve the trading system performance using gRPC. Next, we would like to present our wish list based on our experience with gRPC, Protobuf, and FlatBuffers. And this wish list is not intended as criticism, and rather it's just constructive feedback from the field in hopes of helping enhancing those very valuable libraries. So although we have used 3 threads to work around the blocking nature of stream.receive and stream.send, we believe a set of non-blocking APIs could greatly help simplifying our implementation and further enhancing performance. Additionally, we think an API to provide visibility into the network level queuing it would be invaluable in helping diagnosing and optimizing the system behaviors under load. Although we have transitioned from Protobuf to FlatBuffers, we believe that Protobuf could greatly benefit performance-sensitive applications by allowing this enableable option for developers to pre-allocate memory for one of fields. Also, we believe opening some direct and partial access to the raw buffers could help with scenarios where low-level access of memory is critical. And for FlatBuffers, right now the codec requires a FlatBuffer step builder to be used when building a message buffer, and this in turn gets passed to a gRPC send function. And when the message buffer is received, the received function returns a pointer to the root type of the message struct. We believe it would be advantageous if we can unify those processes to streamline buffer handling. That could make forwarding data received much easier. Additionally, we are hoping that there will be more integration between gRPC and FlatBuffers that, to allow easier access to data fields without the need of extensive code. That will really benefit developers working with performance-sensitive applications. And with that, thank you all for your time.